welcome to this explainer. Today, we're diving straight into Lecture 19 from Skip Uni to crack the C++ compiler's ultimate rulebook for operator precedence. We're going to break down exactly how the compiler looks at a massive, chaotic jumble of math and logic and somehow decides what happens first.
I mean, just look at this code snippet. If you were handed this in a technical interview, would you know where to start? Or would you just kind of panic? How does the compiler possibly know what to do first here?
To demystify that whole process, here's our roadmap. We'll quickly cover the order of operations, run through the precedence hierarchy, look at the associativity rule, solve some practical expressions together, and then leave you with a final challenge.
All right, Section 1, the order of operations, decoding the compiler's rulebook.
So why does the compiler even need a strict rulebook in the first place? Well, precedence and associativity basically act as the ultimate VIP list. They dictate exactly which operators get to go first. Without this definitive, hard-coded framework, every single compiler out there might give you a completely different answer to the exact same math problem. And yeah, that would be a literal disaster for your code.
Moving right along to Section 2, the precedence hierarchy, ranking the VIPs of C++.
Okay, looking at our top-tier VIP list, scope resolution sits at the absolute highest priority. It is the undisputed king. Quickly following that, we've got our postfix increments and function calls. Right below those, but honestly still very high up, are the prefix increments, unary plus and minus, logical not, bitwise not, and dereference operators. Basically, when these guys show up, they skip the line completely and demand to be evaluated immediately.
Now, moving down into the middle priority tier, things get highly competitive. Your basic arithmetic, like multiplication and division, beats out addition and subtraction. But check out what comes next. Arithmetic beats out bitwise shifts, which in turn outrank our relational comparisons like greater than and less than. Then, further down that middle tier, we have our equality operators, followed by bitwise operations, and finally the logical and or. It's like a giant, very specific ladder.
And at the very bottom, we have our lowest priority operators, things like the ternary operator and assignment operators. Honestly, their only job is to just hand over the final computed value once all the heavy lifting is done. Oh, and the comma operator? Yeah, it sits at the absolute lowest priority of them all.
That brings us to Section 3, the associativity rule, the ultimate tiebreaker. So what happens when two operators share the exact same priority level? Say you have an addition and a subtraction right next to each other. That's where the associativity rule swoops in as the tiebreaker. The vast majority of operators normally read left to right, exactly like reading a book. But we do have a few specific rebels that evaluate right to left. For example, if you chain multiple assignment operators together, the compiler actually starts on the far right and works its way backward. Pretty wild, right?
All right, Section 4, solving practical expressions, the proving ground.
Here is our first challenge, pulled straight from the source lecture. We've got a string of equality operators that all share the exact same precedence level. So how exactly does the compiler unravel this?
Well, before we solve it, we need to talk about a vital code-cracking concept, implicit typecasting. When you compare a Boolean to an integer, the compiler automatically upgrades that Boolean to match the integer's weight class. A false is treated as a 0, and a true, or actually, scratch that, any non-zero integer at all, is treated as a 1. Let's trace this step by step like a detective. We see our associativity tiebreaker in action, reading left to right. First up, 5 equals 10 evaluates to false, so our expression is now false is not equal to 20. Next, that implicit cast kicks in, and the false result turns into a 0. Finally, we evaluate 0 is not equal to 20. Since 0 is for sure not equal to 20, it makes the final mathematical statement wonderfully true. So our answer is 1. For our second example, we're mixing bitwise shifts with compound assignment operators. We have a plus equals 2 left shift 1, and for this, let's assume a initially equals 10.
Let's consult that hierarchy. Because the left shift sits higher up on our VIP list than the assignment operator, the compiler calculates the shift first. Shifting the bits of 2 to the left by 1 position effectively multiplies it by 2, which gives us a 4. Next, it seamlessly adds that 4 to our variable using the assignment operator. 10 plus 4 means our final result is 14. Easy enough once you know the rules.
Now let's look at a true interview trap, evaluating logical and relational operators with and without the ultimate VIP pass, parentheses.
These two expressions look nearly identical on the screen, but as you'll see in a second, they behave completely differently.
Let's tackle the top one first. Because of those parentheses, we skip the normal precedence line entirely and solve the inside block first. 5 is greater than 2, so that's true, and the 0 acts as a false. True and false evaluates to false. Then we step outside the parentheses, where that logical NOT operator flips our final Boolean result to true.
But look at the bottom expression. Without parentheses, the NOT operator immediately dominates the precedence list. It applies directly to the 5. Since 5 is a non-zero integer, it's considered true. Flipping that makes it false, turning it into a 0. Suddenly we're evaluating 0 is greater than 2, which is false. That cascading effect completely changes the final answer to false. Literally, one tiny set of brackets changed the whole shebang. Finally, Section 5, the final challenge. Test your compiler logic. Now that we've decoded the rulebook and seen it in action, it's your turn to put this framework to the test. Based on the hierarchy we just went over, how does the compiler evaluate an expression that mixes a bitwise AND with an equality operator? Who wins that precedence battle? And can you successfully trace the final result? Think back to our middle tier VIP list. I'm going to leave you to ponder that puzzle. Thanks for tuning into this explainer. Keep practicing those expressions, and I'll catch you next time.